Okay, Ji, Bismillah Rahman Rahim. Today we're going to be discussing regarding your data packets. Basically, the intention of this topic right here is to understand what a data packet is and what is the basic process of a packet that is originating from one source to its destination over a public network such as your internet. And basically, this is the underlying principle of your packet switching network, which we are currently using right now to transfer a lot of data. Okay? Most of our internet data traffic is regarding our packet switches, and each packet is basically transferred. The principle of packet switching is that, or a packet is that your whole data transfer that you are intending to transfer over the entire network transmission is divided into small chunks known as packets. Now, these packets are by principle traveling on different locations, they're taking different routes, and via those different routes, they eventually end up at their destination. Now, the principle is that at their destination, these packets are assembled to form your complete data, and this complete data is then thereby interpreted by the intended recipient computer. Now, of course, this raises a lot of questions as to what happens when a packet is, say, slower than the rest. Does it reach the destination later? And if, for example, I have, the packets arriving at different times, does that mean the data will be corrupted in some way? Does it become useless in some way? Yes, there are a lot of questions, and these are all valid points considering the fact that we are using a system that does this, that in fact creates different chunks of data known as packets, sends these packets on different routes from your source to your destination. And via these different routes, by principle, each packet may arrive at different times at the intended recipient computer. And it is also possible that some packets may not reach the intended recipient at all, in which case there are special precautions that have to be taken place to make sure that these packets eventually are retransmitted, so that if packet loss is not tolerated, then those packets are retransmitted so that that data can be completed. Secondly, if data transmitted is out of order at the intended recipient, there are also special precautions that are taken with respect to that as well. So if data is being retransmitted, or the data is being transmitted over a packet switching network, if data is arriving at the destination at different times, what happens then? So we'll be discussing that in detail. First of all, let's look at what a data packet is. Essentially, it is a small chunk of the data. Let's assume for a second that we're trying to transfer an image over our public network, such as the internet. Now, this image can be several megabytes, and this image, when transferred over the internet, will be transferred via your packet switching network, as most data over the internet is transferred by a packet switching network. That image of several megabytes is divided into small equal sized chunks. These chunks are known as packets. Now, each packet will be roughly approximately the size of 64 kilobytes, and which is actually quite small compared to the actual size of the data. And apart from the 64 kilobytes, we have additional header and trailer information, which also comprises some sort of size. They add to some size with respect to the original data as well. Now, we'll be looking at what this does. The idea of splitting of data in this way means that each packet can be sent along a different route to its destination. It would be clearly a great benefit if a particular transmission route was out of action or very busy. Now, as opposed to packet switching network, if you remember, we have discussed circuit switching network. Now, what circuit switching network is that there is a source of information and there's an intended recipient. Now, the modes of communication between this source and destination is that there is a dedicated path between the source and the destination. This dedicated path is established initially before actual data transmission can take place. That means that there has to be some sort of initial communication that basically requests the receiver if he is available, if it is available for transmission or not. If there is intended recipient is available for data transmission, only then the sender will start sending data. Now, we see a similar type of communication whenever we're working with, whenever you're using a telephone or landline. So whenever you're dialing a computer on your phone, the person who's on the other end, the receiving phone, the receiver, may may be busy. The phone will be, the call line will be busy. So he might be talking to someone else at that time. And you will see, you will realize this, that when you dial his number, you will see that there is an engaged tone. So basically what you're doing is you're trying to establish a connection. There's initial sequence of seeking permission. This is known as establishing a handshake, initial handshake. Now, once the initial handshake has been established, only then a communication can take place. Now, the way circuit switching works is that there is a dedicated path between the sender and the receiver. This path has been created by several interconnecting nodes, and eventually when the destination computer or device is available for communication, the sender transmits all its data only on this single path. So data transmission is carried on only a single route. This route can be established by using multiple nodes, no doubt, but it is established only through a single route. Now, the benefits of using this technique is that you have all bandwidth of that single route available for you in that communication, all bandwidth. So that means that you have uninterrupted data transfer, a smooth sequence of data being transferred uninterrupted. So if you're calling on a phone or it's a video call, you notice that there's no lag whatsoever. It's a continuous stream of smooth flow of data. But the biggest disadvantage of using this technique is that if that if that circuit is disabled for some reason, say that some interconnecting node in between becomes busy or disabled for some reason, that means your entire circuit, that entire dedicated route between the sender and the receiver becomes completely disabled. And that means that is complete loss of information. So since I'm relying on only one route to transfer all of my data, if that one route becomes disabled for some reason, all of my data is lost. So that is one of the biggest disadvantages of using circuit switch network. That if I have a dedicated link, I am relying completely solely on that dedicated link to transfer all my data. Now, if that dedicated link becomes disabled for some reason, then that means no data is being transferred anywhere. Now, to tackle this technique, over the years, we have developed a technique which is known as packet switching network. Now, packet switching network defies the original concept of keeping data in one piece. So essentially what you're doing is that you're dividing the data into small packets, small chunks known as data packets. Each packet is sent from its source to its destination on different paths, different routes. Now, since we have different routes, if one route does become disabled, that means only that particular packet is affected. The rest of the packets, if they're not, disabled in any way, the rest of the packets, they reach the destination. Now, this is known as packet loss. There's some slight packets being missing. Now, if, for example, packet loss is tolerated in certain applications, it is tolerated. For example, video streaming, it is tolerated. In that case, you will still have most of the data. As opposed to circuit switching, the loss of the route may result in no transfer whatsoever. However, in packet switching, if say one route for one packet is disabled, only that packet is affected, and that packet will not reach its destination. If you want, you can ask for that packet to be retransmitted, and thereby you will have the complete data at the end. Now, it is obvious that it may have its own issues. We'll be looking at that in a bit later. But the first thing it ensures is that there is at least most of the data being transferred. So if packets are being lost, or if data is being lost, it's only a few packets. And a few packets, in most cases, does not have a general effect over the information. Now, of course, certain types of data, such as web pages or documents or stuff like that, or program code, packet loss in that particular scenario may be devastating. That means that that web page will be incomplete, that program code will be incomplete. In that case, you will have to go for packet retransfer. But say if it's an image or a sound file, slight packet loss may not necessarily create a big effect. And most of the time, you might not even realize it. And still, you will be relayed the general information that was intended to be sent to you. Now, this is the basic motivation behind creating a packet switching network, that we want a more reliable means of data transfer between the sender and the receiver. Now, Let's look at what a packet structure basically is. If we look at a packet closely, packet has initially a header. Now each header has these interesting pieces of information. Then there's the payload, the actual information that this is the, if we look at our image example that we divided into small packets, that one chunk of that image will be representing the payload part here. And then there comes the trailer, which is the ending of the packet that signifies that this packet has ended. Now I will explain why this is so important. First of all, let's look at the header. Now, the header has a big question arises that how does each packet actually know where to go from a particular position in the network? Now, how does it find its intended recipient? Well, the simple answer is that through IP addressing. Now, we've studied this before, and we'll look at this concept in more detail later. But basically, IP stands for Internet Protocol. Now, the IP address basically represents it's your unique identification on the public network, such as the internet. So it is through the IP addressing that information that is meant for you eventually reaches you. And if you don't have a unique representation of yourself on the internet, you can forget about ever receiving any information that was intended for you, because no network component will be able to identify you as a unique user of the internet. So IP addressing is that important. So if I am sending a packet, Alice is sending packet to say James, Alice will mention James' IP address. Now, of course, not Alice is directly mentioning it. There are other techniques involved in between, such as your domain name system, so and so forth. But long story short, when that data leaves Alice's computer, it has James' IP address mentioned on it. So based on that IP address of James, that packet will eventually reach its destination, which is James' computer. And obviously, James needs to know where this data came from. That's why Alice's IP address will also be part of the packet. So next time when James wants to respond, they will be able to do so through the mention of the source IP address. So these two pieces of information are part of the header, the source IP address and the destination IP address, where the packet is going, where the IP address is coming from, and where it will be going. Now, these two pieces of information allow this packet to be found on this huge network that is known as the internet, and it eventually reaches your destination. Not always, but when it is a perfect transmission, it will reach your destination computer based on the IP address that is provided. Now, third piece of information in your header is your sequence number of the packet. Now, this is what's important here with respect to maintaining the overall meaning of the data. Now, the image divided into different packets. So that's how we see maybe part of the image, some pixels here, there, so on and so forth. But in reality, what's really happening is that your image is stored in ones and zeros. As we all know, all information is stored in ones and zeros in your computer. That sequence of ones and zeros divided into different packets. Now, again, it's all just ones and zeros. How will I be able to identify packet number 1 to packet number 2 or packet number 3? That is based on the sequence number. And this sequence, with the help of the sequence number, I'm also addressing the second issue of a computer of the data reaching its intended computer. Now, when that data reaches intended computer using packet switch network, as we discussed before, there's a great chance that the data will arrive out of order, which it usually does. Why? Because each packet has its own path from reaching a source to destination. And obviously, when it reaches it follows its own path from its source to destination. That means it will be different arrival times of each packet at its destination, because of which I will have all packets out of order at the receiving computer. Now, to make sure that my data is reassembled into its original form, my receiving computer will follow the sequence number of each packet to compile that data into its original form, and also to maintain if some packet has been lost. And this is very important. If, say, for example, I receive packet 1, I receive packet 2, I receive packet 4, and I'm missing packet 3 in between. How did I know this? Because the sequence states that after 1, 2, there should have been 3. There's only 4. That means packet 3 is missing. So if based on the sequence number, my receiving computer will be able to identify if a packet is missing. And if required, if the application or the type of data, if it's not streaming, for example, if required, I can ask for a particular packet to be retransmitted based on this sequence number. Finally, the fourth piece of information in the size is the size of packet. Now, size of packet is important here because if, say, for example, it is 64 kilobytes as mentioned here, that will be mentioned here as well. Say, for example, during transmission, some data was lost or something happened with the data, changed somehow. It is quite possible the size will also have been changed. So receiving computer will have a sense of what the size of the packet should be. And based on this, if the size of the packet that's mentioned in the header is not the same as the actual size of the data, that means the data has been changed and altered in some way during transmission, and thereby it should not be trusted. Because trusting corrupted data at one point can cause a cascading effect of wherever that information is to be used. Say, for example, that is some stock exchange information. If it's corrupted, that stock exchange values will be used in other applications, wherever that stock exchange application is being used, whatever website is using it will all have wrong information, and everything will be overall, this whole system of the stock exchange will have a very devastating effect. So this is the cascading effect of providing wrong information. That wrong information will be carried forward. So it has to be very important. It is very important that any corrupted or wrong transmission should be identified and taken care of right then and there. So this is one way of doing that over here. So in the next lecture, we'll be looking at the trailers and how cyclic redundancy checks are used for identifying any sort of errors if present in your data transmission. Okay, now let's look at the information. We just discussed what the header information is. And now let's look at what the payload is actually the small chunk of the actual data we're trying to send. And let's look at what the trailer stores. Now, the trailer is actually having two pieces of information here. The first represents what is a method that specifies that this packet has ended. Now, why is this important? Well, actually, if you look at it, you see images in the form of, say, pictures, trees, cars, buses in front of you, right? That's how you perceive information. But in reality, all information stored on computers is just ones and zeros. And whatever information that you're transmitting over the internet is always going to be in ones and zeros, irrespective of whatever it is. So a receiving computer also is just receiving a strong, long, steady stream of ones and zeros. Now, if it's a sound file or if it's an image file, they're all ones. There's no specific difference. We have the sense of these small techniques that separate one piece of information and one chunk of data from another chunk of data so that they don't ever get mixed up. Otherwise, it's just a sequence of ones and zeros. These formats are defined in different applications in computer sciences and computers. They could maybe in the working of instructions in your processors. They could be for IP addresses as well. We're looking at that later. Basically, the purpose of this is to ensure that I know, or my receiving computer knows exactly where a packet has ended, so that if any data is received after this method or this flag over here, for example, if any data that received after this flag is not to be treated as part of this data that I've just received. If I don't have this flag, I will not be able to tell the difference between two successive packets. And maybe packets of, say, different files. And because of this, the whole data may be mixed up and it will lose information. It will lose meaning whatsoever. So I have to be able to separate packets. And if I can separate one packet, I will be able to separate packets for, say, different types of data, different files altogether. So this method is used for that technique specifically. Secondly, there is some form of error checking to ensure that packets arrive error-free. Now, they can be error checking method can be of different types, but one example is discussed here. This is a very simple technique. This is known as cyclic redundancy check, and CRC, we can commonly known as CRC. Now, basically what it does is that the data that is being sent is analyzed and it's counted for ones, only just the ones. So the sending computer will add only the bits that are on, only the one bits. Say it's got 15 one bits. So it will add them all together. It's got the number 15 in it, right? So it's going to count all the one bits and save that value in this portion of my trailer. And it's going to transfer the file. Now, again, this is not a fully foolproof method, but it's a good, it's just a simple way. And it's just one way of possibly identifying if something has gone wrong. Apart from this thing, there's another way to possibly identify if something has gone wrong with the data. Now, if the number of ones arriving are different than the number of ones that has been sent, that means data has changed, data has been corrupted, and thereby it's not supposed to be trusted. So this method over here, this value over here on the receiving side will be compared with the actual number of ones of the packet received by the receiving computer. If the actual number of ones is not the same as the number of ones mentioned in this part of the trailer, then that means this packet has been altered during this transmission. It does not mean there's some malicious intent to it. It can happen to a wide range of reasons. Due to communication line, there's to be some interference in the communication lines, whatever it is. It could be any reasons. But since it happened, I may be able to identify it through this technique. Now, the reason I'm saying I may be identified because it is possible that the number of ones are the same, but the positions has shifted around. In any case, even the number of ones has changed, positions of ones has shifted around. It means data has changed. It's a completely different value, but the number of ones is still the same. So it's not an accurate method, but it's just one method. It's like parity bits. We'll be discussing that later. Now, again, sending side a computer, since it's now data is being sent, is formed into a packet. The sending computer counts all the number of ones in this payload and saves that value over here. The packet sent, the packet reaches from router to router, router to router, and eventually it reaches its destination. At its destination, the receiving computer will look at the header and identify if it is the intended recipient, and will identify if the sequence of packets are okay, so on and so forth. Actual payload is there. Now, the receiving computer will actually analyze the payload, count the number of ones, compare the number of ones it saw here with the number of ones that it sees here. If both values are not same, then the data should not be trusted. If both numbers are same, then it can be trusted, but it's not 100% sure. Maybe the numbers of ones are same, but they have been shifted around. If they have been shifted around, that means it's a different value altogether. But this technique is just one of many approaches that can be used to identify if the data has been corrupted in any way. So this is your basic packet structure. And in the subsequent lectures, we'll be looking at how this packet switching network works, what is the role of the router in it, and we'll be following on with your error checking techniques, furthermore error checking techniques as well.